Well, today we have Yannis Georis here in person at UNSW, giving us a seminar on low-scale leptogenesis. And Yannis is a PhD student. He is about to start the final year of his PhD in October, I understand, and he's working under the supervision of Marco Trevis. A lot of us know Marco, of course. And yeah, so please, and he's visiting, well, he's been visiting for a month now, and is here for another 4 weeks or so. So if you want to come talk to him, he's here. Anyway, you start.
Thanks a lot for the introduction, and also for giving me this opportunity. So yeah, as you can see from the title, I would like to describe a bit low-scale leptogenesis, and kind of the idea is like how can we constrain this both from measurements in the early universe part, but also mostly in laboratory, so colliders or other basic experiments in a sense. So this is kind of different works, and I will be sure that in collaboration with different combination of these people here. Now, starting with the beginning, as I'm sure you all know, I mean, this standard model has been extremely successful, but of course there are a few questions that are still, remain unsolved. And we won't try to address all of these today. I think what I would like to do is really focus on what I think are two of the most pressing questions. The origin of neutrino masses, but also why is there more matter than antimatter in the universe? So, one very simple way to solve this is it's just extending the standard model with right-handed neutrino. It can explain neutrino oscillation data through the type 1 seesaw mechanism, but also can explain the baryon asymmetry of the universe through a mechanism called leptogenesis. So the philosophy that I will guide a bit through this talk is really kind of minimality and testability. We just want this right-handed neutrino, nothing else. And also, we're trying to find a way to constrain them at current experiments or near future experiments. So not waiting for a moon collider or something like that. Now, the outline of the talk is basically the following. I first do just neutrino masses. What can you already say when you only try to reproduce neutrino masses? Then we add this second requirement to have low-scale leptogenesis. I'll explain what it means later on. So again, how does that change? How does the picture that we drew in one kind of changes once you have the requirement to have leptogenesis? And then if I have time, I would like to discuss also a less agnostic scenario. So in the first two, I will just add right-handed neutrino and assume nothing else. But then if you're a model builder, you know that there are many different type of questions that you can also try to solve. For instance, the origin of the flavors in the standard model, and then we'll look how exactly this, again, the constraints that we drew in the first 2 points changes once you have this kind of more model-specific, specific models, sorry. And then I will conclude. So let's start with the neutrino masses. And as I'm sure you all know, because you had lectures on this already a few weeks ago, basically, the way this works, the type 1 seesaw works, is to add these right-handed neutrino with the Yukawa coupling to the standard model neutrino, and then just a Majorana mass, because everything that's allowed should be there. So these right-handed neutrino gauge singlets, they can have a Majorana mass term. So these are the only two terms that you add in the Lagrangian, and then after the Higgs symmetry breaking, you basically create a mass term for these. For the standard model neutrino, which is inversely proportional to the mass of these new states. Hence the name seesaw. The traditional idea was to add very heavy states, which explains why the standard model neutrino was so light. That's the kind of initial picture. Now, okay, probably you all know this. I would like just to emphasize maybe two or three points on the type 1 seesaw. First is one thing is how many of these particles do you need? We have measured 2 neutrino masses already. So just from the matrix structure, you know that you need at least 2 right-handed neutrino to explain the neutrino oscillation data. Now, how many is an open question. There are gauge singlets. There is no theoretical constraints on the number of generation. If you're more driven by minimality, you say, okay, I'm only taking the 2 right-handed neutrino and that's it. So for instance, in the UMSM, you have 3, but only 2 explain the neutrino masses, let's say, are responsible for the neutrino masses. So that's kind of one motivation that has been already extensively studied in the literature. What I would also like to discuss today, and what I've been working on, is this next to minimal scenario. We have 3. because that's also very well motivated in the context of gauge expansion of the standard model. You would typically expect to have 3 right neutrino to cancel gauge anomalies or stuff like that. We don't consider gauge extensions here, but it's just like something that you could expect at least as residual from this gauge extension at low energy. So that's one thing. The other thing, more phenomenological, because that will appear a lot in this talk, is just what I will try to constrain with these parameters u alpha squared, so the sum of the mixing angle basically squared, because that's what drives the number of events that you expect at colliders. Typically, that's what you expect to constrain from collider or fixed target experiments. Okay, now one interesting question is like, what is the mass of these new states? And here we don't really have any good theoretical prior on the mass. Basically, it depends what you're interested in. If you think that if you like symmetry, you can also put the mass of these right neutrino to 0. That's what we call the direct neutrino, but then you have to face a very small recount. If you think that the low energy anomalies are a big thing, then you would typically expect the mass of this right neutrino to be around the EV scale. Again, you can move up the ladder, the energy ladder, and then at the KV scale, you would typically expect that to be the mass of this right neutrino if they kind of attack like a candidate. And if you want to reproduce the baryon asymmetry, you will need something above a few tens of MeV all the way up to the Planck scale. So if you like motivated by gauge extensions, particularly the grand unified theories, you would expect it to be around 10 to the 14 GeV, for instance. Now, there are a few theoretical constraints on the mass. If the only problem is that they all rely on the fact that you would only have right neutrino and nothing else. In that case, naturalness would predict that you should be below 10 to the 7 GeV roughly. Unitarity would ask you to be below 10 to the 15 GeV, and then you also have constraints from the vacuum testability. But okay, these are to be taken with a grain of salt in the sense of it's only valid if you have only right neutrino and nothing else all the way up to the Planck scale. Now, what the kind of range that we are interested in this talk, and that's what we mean by low scale, is really between the MEV and the few GeV, because that's what would be a collider testable in the near future. So the parameter space, what does it look like at the moment? If you only have, you can, as I was saying, you can produce them in colliders and other type of experiments. So here you have the mixing angle with the mu on neutrino. So that's you're coupling to the mu on neutrino, and here you have the mass of your right neutrino. And so this is kind of the experimental status at the moment. Everything that's in gray is excluded, either by direct searches, electronic precision data, BBN, or everything that's below this green bound here is already excluded by neutrino oscillation data. So from the requirement to have neutrino masses, only everything that's in this white region here is developed. And then you have, as you can see here, you have very different type of experiments that can search for them. Below the D meson mass, basically, you have these meson decays, then you have W and Z decays at FCC, for instance, and then above that, you have more virtual W and Z exchange, like at the mu and collider, potential mu and collider. So, okay. So that's for the experimental status. Now, regarding this kind of green band here, that's what we call the seesaw line, and that we will come back. That's the minimal kind of mixing that you can expect. So it just comes from, if you look at this kind of, at the traditional and usual seesaw relation, you can deduce that the mixing should be around of the electron mass, the neutrino mass divided by the mass of your right neutrino. Now that's only valid if you kind of forget about matrix structure. You can always have some kind of very special metric structure. So that's forming a kind of a B minus L approximate symmetry, such that the mixing angle would be much larger, and then you have much better hope to discover them at present day colliders. So basically, the structure is like you have two that kind of have the same coupling and roughly the same mass, and form this kind of pseudo-Dirac pair. And then you have if you have 3 right neutrino, you have a third one that is kind of almost decoupled. And that approximately preserves B minus L, and that can lead to very large production colliders. So that's the typical scenario that, typical structure of the matrix that you have if you lie in, this region of the parameter space where you're much above the screen. Okay. Now you can also, now you can also look at what can you say other than just discovering this right in a neutrino? And one interesting thing that you can do is, if you discover them, measure the ratio, the flavor ratio. So how much of these right in a neutrino decay into a tau, into a muon, and into an electron? Because that will tell you a bit something about the theory that's behind. If you have only two right in a neutrino, basically you're forced to lie in this kind of, for normal ordering, in this red region, that is, and for inverted ordering within this blue region. So that's here the coupling to the tau, muon, and electron. And that changes, for instance, if now you have a non-zero electron, a non-zero lightest neutrino mass. So already by measuring, so here you see the different region. Here it's if you have, like for n equal to 2, like for 2 generation, if you have n0 equals 0, and then you have different regions that are allowed as the mass of this lightest neutrino increase. So already in case we discover them at colliders, and in case we measure enough of them, that we can kind of have good estimate of what's the ratio of decay into muon, electron, and tau.
So this is the right-handed neutrino.
No, this is the this is the right-handed neutrino. So this is
what is massless right-handed neutrino?
No, massless limit for the lightest neutrino. For the
lightest regular.
Yeah, the standard model neutrino. Sorry. Yeah. So we only know that the mass splitting between 1 and 2 and 2 and 3. So basically, there is already, since if you want to reproduce neutrino association data, the kind of Yukawa coupling of your right neutrino will depend on the kind of spectrum that you have in the standard model states. And so that's what you see here. And if you're lucky, by measuring something here, you can already exclude the lightest neutrino mass being 0. So I will come back to this later after we do leptogenesis to really show how much can we exclude it. So that's it for this kind of quick review. I will come back to some part of it once we do leptogenesis. But basically, measuring all these ratios will tell you something about the UV part in a sense. Okay. Now leptogenesis. Start again by a quick introduction, and as I'm sure you all know, in order to have successful generation of baryon asymmetry, you have 3 conditions that need to be fulfilled. One is C and CP violation, the other one is deviation from thermal equilibrium, and then after that you also have to violate the baryon number. Now, in the standard model, the C and CP violation and deviation from thermal equilibrium, they're not present in large enough quantities. Because the C and CP violation quark sector is just too small, so you need some additional source for that. And the right-handed neutrino can serve that purpose, because if the Yukawa coupling is complex, you can have CP violation when they oscillate or when they decay, and then of course when they will freeze in or when they will freeze out, that naturally kind of provides some deviation from equilibrium. And then, so here is the kind of spectrum. Either you can produce the kind of a CP asymmetry in the freezing part or in the freeze out. Now you also need baryon number violation, and that is provided by, just as in the standard model, by the Weeks-Faleron process. That also gives you kind of already a timeline for when leptogenesis must happen, because the Weeks-Faleron process is only active between 130 GeV roughly and 10 to the 12 GeV. So you have a cutoff. You need to produce your baryon symmetry before the Faleron freeze out at 130 GeV, because otherwise you cannot reprocess the lepton asymmetry into a baryon symmetry. So that's actually a very, that's what will be one of the main limiting factors of how much low scale you can go with leptogenesis. Now, the initial idea of leptogenesis, that's what we call vanilla thermal leptogenesis. So it was invented by Fukuyama and Yanagida in 1986. And I mean, the way it works is the setup is basically the following: you only have an asymmetry generated by heavy neutrino decays. One heavy neutrino decay, you have very large hierarchy in the mass. So one is very much lighter than the other one. and then you have something unflavored, so you just neglect the decay into some one combination of the lepton flavor, and there is no lepton changing, flavor changing process in a sense. And so basically, then what you have to do is just like for dark matter, you solve a set of Boltzmann equation, one for the density of your right-handed neutrino, and then one that kind of tracks the evolution of the B minus L symmetry. So you get these kind of plots. They will reach the equilibrium here, and then they will decay at some point, and during this decay, they will produce some B minus L symmetry. So that's the way it works, and it crucially relies on this parameter that we call the decay asymmetry, which is basically the difference between the decay into leptons and the decay into anti-leptons. So that's the kind of crucial parameter here, and you can compute it by just computing the interference between all these diagrams here. Now it was done, and unfortunately, you can show that there is an upper bound on this decay symmetry as a function of the right-handed neutrino mass, and that may actually kind of set a lower bound on the mass of your right-handed neutrino. This scenario cannot work for something that is lighter than roughly 10 to the 9 GeV. So it's an approximate kind of a lower bound. So that, of course, is not very good when it comes to direct detection. So we kind of want to find loopholes. And of course, the loopholes, you can already see them here in the three assumptions that we have seen. Now, so people have looked at this for a long time now, already 2 decades. You can basically already push that a bit if you take into account flavor effects. But the game changer here is like to go to lower masses is to have a kind of a small mass splitting, for instance. I mean, I will come back to this, and that's the scenario that we call low-scale leptogenesis. So there you can push it to a few tens of MeV, as I was saying, and that's the kind of scale that I would be interested in. So you have, traditionally, you have 2 different types of scenario. ARS leptogenesis, where you produce everything during the freezing. So basically, you produce your right-handed neutrino. They will oscillate, but because you have a coupling complex, you have some CP asymmetry that arise from there. I mean, only some flavor asymmetry, and then you need some washout that acts at different speed in every flavor to kind of produce a total baryon asymmetry here. And then you have resonant leptogenesis, which is in a sense much more in line with the thermal leptogenesis scenario. You still have just a decay of right-handed neutrino, but this time you have multiple right-handed neutrino with very small mass splitting, and that kind of resonantly enhance the CP asymmetry. So these are the 2 different types of scenario that were traditionally studied, and for a long time it was thought that ARS leptogenesis would only work for something that is below the W boson mass. The easy reasoning for that is just that if it's above the W boson decay mass, then you enhance the decay cross section by a lot, and you would just reach thermal equilibrium very quickly. And then for resonant leptogenesis, the people thought that it would only work for masses above 130 GeV because basically below that, since there is this Talleyrand freeze-out cutoff at 130 GeV, they would just not decay because the mass would be smaller than the temperature. Now, that's very, let's say, hand-wavy reasoning. In practice, you really have to do the numerical solving of this equation to be sure of what's the parameter space. And what was done in the last few years, and what people realize is that really you have to see these 2 scenarios as kind of 2 regimes of one unique model. So basically, they can be described by the same set of equation and the parameter space where they work kind of overlap. That's what, I will come back to this. But yeah, they can basically be described by the same set of quantum kinetic equations. So it's kind of a generalization of the Boltzmann equation, but in order to include the oscillations of your neutrino. So I won't go into too much detail here, but just to describe the structure of this equation that you have to solve is you have evolution equation for these density matrices for positive and negative density right-handed neutrino, and then one equation for this lepton asymmetry here. And then you have one term for the oscillations, which is encoded by some effective Hamiltonian that you have to compute. And then a few terms for basically the damping rates. So that's the interaction rates of your right-handed neutrino. So it's just, the structure is very simple, oscillations, and then interactions. And okay, of course that's the schematic level. I mean, it's quite tricky in practice to compute these Hamiltonian and interaction rates at finite temperature in full generality, because you have many different finite temperature effects, and so for already 20 years now, people have looked into this and try to compute with more and more accuracy. And the picture, I mean, now it's starting to converge, and I think it starts to be quite reliable in that regard. So that's it for this kind of long-ish introduction. Now, what we have to do is basically solve this set of equation for every point in the parameter space and see what's consistent with leptogenesis. So that's what was done by these guys here, Misha Shaposhnikov and Ignacy Yazov, for the parameters. I mean, for the case where you have only two right and a neutrino. So here on the y-axis, you have the total coupling of this right and neutrino, and on the x-axis, you have the mass. I mean, that's the average mass because the mass degenerates. So you just quote one mass here. They all approximately have the same mass. And what you can see is that leptogenesis is possible within these lines. So everything that's in blue is already excluded. And here it's because of neutrino oscillation data, here because of BBN, and here it's the constraints for leptogenesis. So what we see is that there is already a sizable space that is load and will be probed by a ship by CCAE in experiments. Now, also what's interesting is that as I was saying, the parameter space for both freezing leptogenesis, so this ARS type that I mentioned earlier, is kind of overlapping, as I was saying. So that's the green line here. Sorry, the red line here that you see is the freezing part. And the blue line here is the freeze-out part, the one where you only have the decay. You can see that they kind of overlap. So it's really, ARS works low mass better, resonant leptogenesis works at high mass better, but there is clearly a regime where both, I mean.
How does it over? So, I mean, there are two different coupling regimes, right?
So there are, I mean, here the scenario are different in the sense that like this, so what we call here.
So what does freezing mean?
Freezing means that you
start off
with nothing
out of equilibrium, and then you
so you start with right and neutrino that are vanishing, have a vanishing abundance, zero right and
populate it,
and then you populate it, and then they will
decays.
decay. So that's why actually the freezing part is. I mean, when you start with zero, the total parameter space will be this, all of this, because you start with nothing, and then at some point when the mass is sufficiently large, you will always reach equilibrium, and they will always decay. So in that part, most of the asymmetries produced during the decay. Here it's mostly during the freezing part. Yeah, and then you can look also for inverted hierarchy, and there the parameter space is a bit larger, but overall the parameter space is kind of similar for both. There is also a connection between you can make a connection with this flavour ratio. So basically, if you measure something with very large value of the with very large value of the mixing angle, you can connect it. I mean, they're more likely, and if they're consistent with the leptogenesis, they're more likely to be extremal in the flavour ratio. Usually, it's good to have flavour ratio that are very hierarchical, because that's what I was saying before. You need washout of this asymmetry that are very different between the different flavors to generate baryon symmetry. So that's something that you can already kind of see if you discover them at colliders. But that's, of course, very dependent on, I mean, that's only if you have two right and a neutrino. It's less the case when you have three. So that's, okay, that's one example. That's the case that was already quite well studied with two generations. So what we did with my supervisor is to look at what's happening when you have three generations of this right and a neutrino. And what we observed is that, so the parameter space now that is consistent with leptogenesis is everything that's within these yellow lines. So here and here, and you see that compared to the blue lines are for n equal to 2, so the two generations, you see that you gain orders of magnitude. And the reason for, so that's actually very good for testability. And the reason for this enhancement is that you have this third state that is completely decoupled, which means that it can produce an asymmetry very late, just before the spheron freezes out. So when you're in this B-L approximate symmetry, you would typically produce kind of backlog the production of your asymmetry until just before the freeze out, and then you have less time to wash out your asymmetry by inverse processes like inverse decays and stuff. So that's the basic idea behind why you gain such such many orders of magnitude in the coupling. Okay, and then we also, you can, so yeah, something I did not say before is like the continuous line is when you have vanishing initial conditions, and then again the dotted line is when you start with thermal equilibrium. So if you assume that, I don't know, you have additional gauge interactions at very high scale that keeps your right-handed neutrino in thermal equilibrium, you would typically expect to start with thermal initial condition. We don't consider additional interaction, but that's why we consider this kind of other type of initial condition. Yeah, so you can look at what's happening, also the dependence of this parameter space on the lightest neutrino mass. But here the dependence, it's a bit smaller when you have 0.1 electron volt instead of 0 electron volt. So there is a slight dependence on 0, but it remains in any case orders of magnitude better than when you have only 2 right-handed neutrino. So here again, you can see this transition between something where freezing dominates to a scenario where freeze dominates. We were discussing. Okay, so the great thing about this enhancement is that now potentially we can not only discover this right-handed neutrino, but we can also test leptogenesis. So what do I mean by this? What I mean is, so you have this parameter space. So basically we have a lot of 33 parameters because you have some hidden in the PMNS matrix, in the light neutrino mass, the heavy neutrino masses, and then some rotation matrix. So the idea is like, try to measure these parameters at colliders, let's say, and then if we produce enough of them. Of course, that's if you only see one, that will be difficult. But if you produce enough of them, you could potentially measure them, all of these parameters, and then feeds that back into the set of quantum kinetic equation that you have to solve and see if you still reproduce the baryon symmetry. That's one way to test the genesis. The question is, of course, how much can we do this in practice? So how can we constrain all of these parameters here at colliders? And so we did this. One thing that we can already try, as I was saying, is constraining the light neutrino mass. So so
what's the collider signature? Is it just missing energy and plus some?
No, it will depend on the mass range. Typically, at low masses, you would have displaced vertices, and so that has very low standard model background. So that's why it's in principle something very nice to look for. So I would say at least below the W boson mass, that's the main signatures. It would be a displaced vertex, and then you have same sign dilepton or something. Depends a bit on you have different signatures. But there have been also missing energy searches, but that typically now we can do much better. I think the initial, in the 90s, like PS 191 and stuff like that, they were doing peak searches, but now it's mostly okay. So I think what we do is simple analysis. So we're not pretending to be. You don't have to take all the numbers at it's got at face value. We just did something where we were trying to constrain all of these parameters that are hidden in this type of seesaw, so 33 parameters. As I was saying, the number of events is basically governed by this U squared here, and basically mostly governed by this parameter gamma. That's a lot of introducing a lot of notations. But why do I bring this up? Is because normally you would expect that if you have 3 right-handed neutrino, the sensitivity would be much worse than for 2 right-handed neutrino because you have such a large parameter space that you would kind of be lost there. However, the flavour ratio here, they have a different structure when you have 3 right-handed neutrino than when you have 2. Here you have only terms that are, let's say, arising at order 1 over epsilon, where epsilon is basically how much above the seesaw line you are. So it's basically the number of events, and then terms of order 1. When you have 3, you have terms of order 1 over epsilon, 1 over square root of epsilon, and order 1. So you have kind of you have access a bit more quickly to different parameters here in your theory. Because the leading order here are only sensitive to like gamma, to the mass and some other parameters, but you're not sensitive to everything.
So producing through Drellian? I mean, how are you producing these objects?
So we're producing the, like here, this scenario that we're thinking of is just FCCEE, so electron position, and then you're producing to the Z boson decay. And then typically the number of events will be sensitive to this basically proportional to 1 over epsilon. And so this kind of power counting tells you how much can you expect at each order to reconstruct from these 13. So you have a larger, okay, maybe that was a bit complicated here, but the takeout is like you have a larger parameter space, much more dimensions. On the other hand, you have access at parameters at a lower order in a sense. So you maybe can hope for better parameter reconstruction when you have 3 right-handed neutrino. And so we did this kind of simple analysis where we just look at the number of events in each channel, just looking at how many events do you expect that would couple to the electron that you can see at FCCEE, neon and tau, and then try to.
So this is what cross. So this is FCCE 3 TeV.
FCCEE.
What energy?
Neutral state, so the Z-pole run.
Oh, it's a Z-pole.
The Z-pole run, assuming 10 to the 12 Z boson. So normally that's valid for FCCEE and CPC because now they have, I think the design is the same. But I mean, I should say we're doing something very simple. I mean, we don't take into account any texture stuff. It's really just a chi-squared based on a number of events. So we're just looking at statistical errors in a sense. So we assume some number of events, roughly 10 to the 5. That's let's say on the good side. Of course, you have to be a bit lucky. But that's not crazy. We don't fine-tune anything here. So we assume 10 to the 5 event. We just look at the number of events in each channel, and then we compute kind of a statistical chi-squared to see what would be how could we constrain. For instance, here it's the mass of your lightest neutrino. And so with this kind of simple analysis, what we saw is that in principle, if you want something in constraints at 3 sigma, even with 10 to the 5 event at FCCEE, we would only be able to constrain the mass of this lightest neutrino to be smaller than 0.0809 electron volt, while the constraint by Planck here, so here it's inverted hierarchy, would tell you that it should be lower than 0.015 for inverted hierarchy. So we cannot beat Planck. However, if you know, that's kind of complementary because we're looking at colliders and not kind of, we don't depend on any cosmological uncertainties. So you should probably compare more to Catherine. And in that sense, we're doing this could be a bit better. Of course, there are many assumptions like 10 to the 5, maybe we won't see that much. So I'm not saying that, Catherine is definitely needed, but it's something that you could already test at colliders in the sense the value for this M0. So that's assuming that the true value was 0 electron volt. Now you can also assume something a bit different, like what if the lightest neutrino mass is not 0, but something a bit different from 0, and assuming that you're, assuming some flavor ratio that are outside the typical M0 equals 0 region, and we would be definitely able to exclude at 3 sigma the M0 equals 0 region. So that's something that you could do at colliders. Of course, that relies on quite a few assumptions here. You can also try to do this for every parameter. So basically, do this simple analysis for every parameter that you have in your Yukawa coupling. So that's just okay. They don't have any physical interpretation per se. All of these, it's just a parameterization of your Yukawa coupling, and some of these you will. What we showed is that for some of these, you will be able to really constrain them at a very good level, while for others of them, for some others, for instance, like this θu2, you would only be able to tell some correlations with the Majorana phases or something like that. So even though in theory you could reconstruct everything at colliders, in practice, even with 10 to the 5 events, for some of these parameters, you would only be able to extract correlations for one or two of them. So that's okay. being very bit hand wavy here. That's one way you could test leptogenesis at colliders, is like try to, if we see enough of them, try to extract the parameters and then feed that in back into the kinetic equations. What we also looked at is what you can do with neutrino-less double beta decay. So as probably you know, since the neutrino are Majorana particle, in principle you can have this kind of process where you have two beta decay that happens simultaneously, but without any associated with without any associated neutrino. And in principle, I mean, this is mostly sensitive to the light neutrino contribution, but if the mass of your right neutrino is below 2 GeV roughly, a few GeV, you would have also contribution, direct contribution from your right neutrino to the neutrino-less decay amplitude. And so that's something that, again, you could kind of probe that would tell you basically something about either the mass splitting of your right neutrino. So here we're doing a case where you have only 2 right neutrino, so not 3, because that was already not done before. So you have basically these right neutrino, they can both suppress or enhance the neutrino-less decay rate depending a bit on where in the parameter space you lie. So it's not very clear at the moment what the effect will be, but you can use that to constrain the mass splitting in some of the Majorana phases, but also some of the high energy phases. So for instance, this omega that we see before, you can use neutrino-less decay to constrain that. And so what we saw is that, so here we're seeing basically the constraint that you can put. So on the y-axis, you have the value of the mass splitting. So mu is the relative mass splitting times the coupling to the electron neutrino. And on the x-axis, again, you have the average mass. So the constraints are much better when you have inverted ordering. So basically, below 10 GeV, they actually dominates over the coupling, the leptogenesis constraints, at least in this plane. That assumes, in the plane mu times UE squared. Of course, I can always dial down the contribution to neutrino-less decay by making the mass splitting very small. So that's cannot do, but if you can kinematically resolve this right neutrino, then there is a chance that it gives that neutrino-less decay give some constraints on the parameter space. And I think most interestingly is if you do not observe neutrino-less decay in the next generation experiment, so next generation in 100-time improvement compared to the current sensitivity, then you would be able to, at least for inverted hierarchy, to force this coupling times this mass splitting times the electron coupling to lie in these kind of small bands. So if there is only right neutrino, and if we know that it's inverted hierarchy, and then you know that basically this kind of parameter here should lie in this band here. So that's kind of very powerful, and that's just because next generation experiments will exclude inverted hierarchy if we don't see neutrino-less decay. So in that sense, you need right neutrino to lower, to kind of enhance the lifetime. So that's basically the idea. That's why you're forced to lie in this kind of bands. For normal hierarchy, unfortunately, since the typical band is already 1 or 2 orders of magnitude below the inverted hierarchy one, these constraints are much weaker. So these are 2 examples of what you can do. So using low energy colliders or let's say laboratory experiments to give a complementary view on the leptogenesis parameter space. Okay, so I think I have 15 minutes left. So I've been talking for a long time now. So just the kind of halfway summary of what I've been doing. Right neutrino are a very good probe of, good solution for the neutrino mass problem in the baryon symmetry problem. And if you have 3 generation of them, you drastically enhance the parameter space that is consistent with leptogenesis. Now, and that means that you can produce enough of them at colliders, like 10 to the 5, to not only discover this right neutrino, but also use the information that you can deduce from laboratory experiments to also kind of test leptogenesis. So deduce the value of some of the parameters and then see if it's still consistent with the baryon asymmetry once you plug that back in, into your set of equations. Okay. So that's it for the kind of agnostic part. Here, what I did, I never assumed anything about the right neutrino except that they have a Yukawa coupling in the Majorana mass. You can also do this analysis with now, in the more specific models where the Yukawa coupling are constraints by flavour symmetry or something like that. So that's what I will do in the second part, but since I have 15 minutes left, I'll probably be a bit quick. So if you remember from, first of all, why do we want to, we want to look at flavour symmetries. Why is that interesting? The typical question that you would want to ask is why do you have 3 generations with the standard model? Why everything would be perfectly consistent with only 1? You also maybe want to explain why there are such large hierarchy in the CK matrix. For that also you might need flavour symmetry, or why there is hierarchy in the fermionic mass spectrum. And what we will be interested in today is the form of the PMNS matrix. So why do the neutrino mix the way they do? In particular, why this PMNS matrix is so close to what we call a tri-maximum mixing. So that was one of the driving observation for the field. And so you have seen already, if you were there 3 weeks ago, I think, when Claudia gave a talk, that's essentially we starting from the same model, but we're looking at what's happening for leptogenesis. How does that change the constraints on the parameter space? So the model, I won't go back again all the details. I think she does much better than I do. But basically, the idea is like you have a discrete symmetry of high scales. The group here, GF, with the CP symmetry, and that will break into 2 different symmetry in the charge lepton and neutrino sector. And so she went into a lot of details last time. In practice, there are many conditions that you can that you need to impose on your flavour symmetry in order to reproduce the oscillation data. For instance, you want something that is not abelian, because if it's abelian, usually you can only explain hierarchies and not. We don't have any hierarchies in the PMNS matrix, so that's not a good solution. So we'll not redo all the motivations again. I think I will just kind of give the scenario that we're considering. We're considering this scenario where you have as flavour group delta 6 and squared, which is kind of the minimal thing that you can do. It includes, for different ends, it includes A4 or S4. So that's really probably the minimal and most general group that you can, not most general, but like a very general group that you can use to constrain this PMNS matrix. And that basically gives some very clear prediction to what should be the form of your PMNS matrix and what should be the form of your Yukawa coupling. So in principle, in this scenario, you have to introduce additional scalars at high scales, all these flavors and stuff like that. What we consider here is that everything of this sort happens at very high scale, and we only look at the imprint that it left on the Yukawa coupling. So all these scalars, they have disappeared, they don't play any role for leptogenesis. What changes is, the only thing that changes is this Yukawa, the form of this Yukawa coupling. So the interesting thing here is that you reduce the parameter space from 13 to 6 or 7 parameters, depending on the scenario. So that's kind of much more easy to handle and to analytically understand the parameter space. So I won't go into too much details. There's 4 different, qualitatively different scenarios that we call case 1, case 2, case 3A, case 3B1, depending on which group generator you take to generate this sub-symmetry here, Z2 and Z3. That's not, I will only focus mostly on case 1 here. As I was saying, you have only 6 or 7 parameters. One that is basically the group, let's say, encoding your group theory. This theta R here is basically encoding how many events you expect at collider. So that's this U squared that I was mentioning earlier. Then you have the 3 random neutrino mass, and then the lightest neutrino mass here. So that's basically the only parameters that there are. And yeah, one of the nice things, as I was saying, is like you have an analytical understanding of everything. You can, for instance, relate all these low and high energy scale phases. So you can relate, for instance, the Dirac and Majorana phases to the group theory parameters in a very direct way. So you have much clearer prediction in a sense. And that you can see if you look at this flavor triangle that I was showing you earlier. So that's the coupling to, again, to a neutrino, muon, and electron. And you can see that instead, so before, basically the triangle was fully covered. When you have here, you have the electron mass, the lightest neutrino mass. And in the case when you have 3 right and neutrino, in principle, almost all of the triangle is allowed. With these flavor symmetries, you only have a line that is allowed, at least for this case one. For the other cases, it's a bit less predictive, but basically, in all of them, you reduce the allowed region, the allowed ratio between electron and neutrino drastically. So you have this enhanced predictivity and branching ratio are completely fixed. So again, if now I do the same analysis as before, if you do the same analysis as before, you produce a lot of these particles at colliders, you kind of do this kind of simple chi-squared analysis, you will be able to exclude or confirm and at least give a hint whether these models are correct or not. Because here, if you can measure the flavor ratio at person level, you can basically tell whether or not you lie on this line, and you can directly exclude case one if it's not the case. Okay, that's the other one. There are small regions here, but it's still much better than the agnostic one, as you could probably expect. Then you can also, as I was saying, you can also analytically understand the behavior of the baryon asymmetry as a function of the parameters of your theory. So here in this set of equation, I did not detail too much, but in this equation for the behavior of your lepton asymmetry, you have one term that is the washout term here, and then you have the source term. And if you solve your set of, this set of equation here perturbatively, you can kind of define what CP violating invariance that basically will give you the parametric dependence of your baryon asymmetry. Because that leading, for small Yukawa coupling, the baryon asymmetry will only be sensitive to these 3 combinations. And so, for instance, I can highlight this. So, okay, here it's the one that is only lepton flavor violating. You would expect it to be dominant, to have a huge impact at low masses. This one violates the lepton number, so you would expect to be dominant at higher masses, for instance. And then this one is, violates the flavor number in a sense, even when the mass splitting is 0. That's because you have mass splitting that are induced by thermal effects in a sense. So just to give one example, I won't go too much into the details here, but for instance, for this case one and one chart of parameters, you can see that all of these coefficients, the proportional cosine 3 phi s. Phi s is this group theory parameter. And indeed, if you plot the baryon asymmetry as a function of this parameter, you would reproduce quite well this dependence on the group theory parameter that you expect. So you can make now correlations between the Majorana phases, because essentially this is the Majorana phase, and your baryon asymmetry. And you can do this with another choice of parameter. Then you have sine 3 phi s. So the problem is that you have a lot of discrete choices for whether these group theory parameter are even or odd, and a lot of different cases to investigate. And again, we reproduce quite well the dependence that you expect from this CP violating invariance. So that's one good thing, this connection between Majorana phases and the baryon asymmetry. Another thing is to look now, marginalize over all of the parameters and look at the parameter space that you can have. So here we have the coupling to muon, and here again the mass, and that's the parameter space that you have access. That is consistent with leptogenesis, is basically within the green lines. So all of this here. If you have vanishing initial conditions, and if you have thermal initial condition, it's within these blue lines. And so again, there the parameter space, you basically lose a few orders of magnitude compared to the agnostic scenario However, you remain testable by, at least in this low energy part, you remain testable by most of the most experiments like SHIP, FCCE, or CMS and Atlas.
Is the LHC displaced current limits or are
no,
they...
the current limits, so it's in gray. So everything that is current is in gray. LHC displaced is the one after the high lumen HC.
No, but you also have a HLH. Oh, that's the prompt. Okay.
Yeah, so that's the so that's the displaced part, and that's the prompt part. The CMS and Atlas one, they just here and they're improving every year they have new analysis, but it's still much below the high lumen HC one. So that's one thing here. So basically, roughly the parameter. I mean, for all of these cases, the parameter space is roughly of the same order. So you have 2-3 orders above the seesaw line that you have access. That is consistent with leptogenesis. I think one interesting scenario that I was mentioning earlier, and I will just come back to show this. So here in this case one, you had this C deg that was equal to 0. So C deg was this kind of CP validating combination. This is non-zero even if the mass splitting is 0 at the Lagrangian level. And so as I was saying before, actually, since you're in the finite temperature, plasma at finite temperature, you have correction to the mass of your right neutrino, both from just from the Higgs, but also just from any interaction with any particles. So you have the thermal mass basically picked up by your right neutrino, and this is actually enough to generate mass splitting that is large enough to do leptogenesis, basically. And so that's what you can see here. Oh, sorry. That's what you can see here. So that was already studied in 2017 by Marco's group at the time. You have this basically here. You can see the coupling again, the total coupling to sound the neutrino, and here the mass splitting. You can see that. So everything that's in blue here is consistent with leptogenesis, and basically you can see that there is still a sizable parameter space even when the mass splitting in the Lagrangian goes to 0, because this mass splitting here is enough. And so we also investigated a bit that case. So here is one example. I'm not sure you can see here. You have the mass splitting, the relative mass splitting, and here you have the baryon asymmetry. And again, we kind of see this kind of dependence where the baryon asymmetry for different choice of theta r. So theta r is the value of your U squared, basically. So the value of your coupling to sound neutrino. And it doesn't go to 0. You can still reproduce the baryon asymmetry even when the mass splitting goes to 0. So that's one thing that we have confirmed, that it's still possible within this kind of flavor symmetry inspired scenario. However, since it relies on thermal effects, you need it's also only viable for masses that are above 10 GeV. So it's much more constraints. The total parameter space is much more constrained because the mass splitting is smaller. So it only works for masses above 10 GeV. So I think I will conclude on that slide. Just to summarize what I said before, right and neutrino are a great solution to baryon asymmetry and also the origin of neutrino masses. Something that we did, a line of research that we did with my supervisor, is to investigate the scenario where you have 3 generations, because that was not done yet. And what we found is that the testability is in principle much better in that scenario because you have much larger coupling that are consistent with the leptogenesis. And you can, in principle, you can see enough of them at colliders, not only to test, but really not only to discover there's a heavy neutrino, but if you're lucky, you really test leptogenesis because you would produce 10 to the 5 of them or something like that. And then we also investigated some flavor symmetric version of this type 1 seesaw. And as we could expect, this model is very predictive. And both models are very predictive, but still testable. So if the parameter space still remains large enough that you can, in principle, see it at discover it at FCCE or something like that. And then finally, some nice, I would say, maybe an intuitive feature is that leptogenesis, even if you have mass splitting that are exactly zero at the Lagrangian level, you can still, it's still viable just because you have Higgs and thermal effects that will create some non-zero mass splitting. Thanks a lot for your attention.
Questions? Here or online?
Michael Schmidt?
Yep.
Hi, can I ask, can you go back to slide 37?
Yeah.
Yeah, okay, so the first question is, what is VIC and TIC? What are the two differences? I missed it.
VIC is the vanishing initial condition and TIC thermal initial condition. So basically, for the green part, I mean, everything that's within this green band is consistent, even if you start your simulation with no right-handed neutrino to begin with. And if you start with them in thermal equilibrium, then you only have what's allowed within the blue region, basically.
Okay, good, thanks. One more question on that one. So okay, of course, with the flavor symmetry, it's the parameter space is limited. So what is mostly causing that? Is it due to relations between the mixing angles, or is it due to the phases? Is it mostly the phase? That's basically what I'm mostly wondering.
I would say it's probably, so okay, first of all, I don't have a definitive answer on like exactly what would cause this. So I would, the phase definitely play a role.
So the question would be, maybe you have to ask Claudia there, but so the question would be kind of, if you wouldn't impose a CP symmetry in the flavor symmetry, would you still get that large reduction of parameter space, or do you have much more freedom because you can get a dilation?
Okay, that I'm not completely sure how it would. I mean, if you don't have, you mean if you don't have this cross CP in the group, whether that. Okay, that I'm not completely sure how it would impact the. I mean, the main reason why we have this decrease in the parameter space is because we have the. I mean, we have you have more constraints on this this kind of lepton flavor violating, lepton number violating CP invariance in a sense. So I would say that I'm not completely sure how that would change if you don't have the CP. So I would. So if you remove the CP, I guess you have more freedom, right? So
you certainly have more freedom. The question is what is kind of what's constraining you more. That's I'm just curious.
I would expect definitely the parameter space to be larger, because if you have less constraints on this, you would definitely be larger. How much I would not be able to tell. I think as long, I mean, I agree, one important thing I think is less the triangle plots. I mean, these ternary plots that are here. You have very large constraints on these triangle plots here.
But in the triangle plot, you plot absolute magnitudes, correct?
Absolute magnitude for you. Yeah, I mean, it's you don't have the phases. It's like the sum of the absolute value of the mixing angle. So you don't see the phases, but the phases, like for instance, the Majorana phases, you can still you still have interference between different terms in the mixing angle that such that you're still sensitive to the Majorana phases in in these triangle plots. So I would not say that the phases. I mean, the phases are definitely still. I mean, you still see the effect of the phases on the shape of these triangle plots. So I would say that if you relax now the discrete symmetry, I would definitely expect that you have larger part of your let's say larger parameter space consistent with the symmetry in this kind of ternary plot here. So I would expect that the parameter space for that reason enhance quite a bit. But now quantify this more specifically, I would not be we're doing performance analysis on that.
Okay, good. Yeah, thanks a lot.
Any other question? Here, online, here, no? Anyone online? I have one question. So with your kinetic equations, did you like solve a full momentum dependent set of density matrices, or did you just pick one representative momentum and then you say, okay,
So
this will check
we
that?
average over the momentum.
You average.
Because so people have looked into this. This Finnish guys, Kimmo Kannainen, and they solved the full momentum dependence.
Yeah.
But my impression is that the difference is not huge. Like, okay, for now it's too slow to be able to do this for this large parameter space scan. It's possible for like specific points, but yeah, I would not expect this to have a huge impact on the.
Because normally, I mean, if you don't have the oscillations part, you just have the the anti-commutator part and all the rest of it. Usually quite harmless, I would say, if you just average or pick one representative momentum.
Yeah.
But once you do oscillations, sometimes you have these weird in medium resonant whatever structure, and then you end up having a totally unsmooth.
Yeah. So you can see. Okay. Yeah. Okay. For instance, for the new MSM, I know that it's important. Like if you want to have this resonant production of white matter, there it's very important. Here we don't rely on. I mean, we still rely on this resonance.
Yeah.
But I think it's less problematic. So I think you see the effect. If I remember correctly, the paper, you see the effect in the behavior of the total baryon symmetry. You have some oscillations that you don't see when you kind of average over. So that's what I remember. But I think order of magnitude wise, it remains it doesn't change too much.
Yeah.
I would say mostly because we rely on resonances, but I don't think we need. I mean, for this terrain production, you really need very small mass splitting. Like we need to have almost zero mass splitting at one particular point. We don't rely. I don't think you ever reach that kind of level of resonance here. I mean, at least we don't rely on that much. So that's why I would say it's less problematic. I mean, now if RHN neutrino are discovered, I think definitely we should, make sure. I mean, but for
technically, this is the same as the Forte piano code.
Yeah.
But I mean, and they have done a scan for these light sterile cases using the Forte piano code. They had triangular pulse, but they were doing it for like electron volt scale sterile neutrinos, of course. But no, that's fine. If Kimmo's on it, then he knows what he's doing.
Yeah, I think the main problem is really, I mean, so I think now it's figured out. I mean, it's not conceptually, I think, difficult. I mean, in principle, you can do it. It's just the numerical power. You have to invest a lot of time. And for this parameter space scan, at least to me, it seems that it's not yet worth it. I would say if now we discover them, of course, then you really need to put some power to have a comprehensive understanding of what's happening. But at the moment,
Anyone else? Any other question? Something. No one else online?
Iron divergence cancel.
Iron divergence, yeah.
How do you answer?
No, I'm joking.
Okay, then in that case we will.
Okay.